the most powerful space telescope ever built, turned its gaze toward Mars, and what it found is deeply unsettling. This was not supposed to happen. The James Webb Space Telescope was designed to look far beyond their solar system. Its mission was clear from the start. It would study the first galaxies ever formed. It would capture light from the edge of the universe. It would look back in time, billions of years into the past. Mars was never the main target. Yet scientists made a surprising decision. They pointed this advanced machine toward a nearby world we thought we already understood. A cold desert planet, a place humanity plans to visit next. And that is where things began to change. Because when Webb looked at Mars, it did not just confirm what we knew, it revealed details that older missions could not see. It exposed patterns in the atmosphere. It detected chemical signals with a level of precision never achieved before. And some of those signals raised serious concerns. This telescope does not see the universe like human eyes. It sees heat. It sees invisible light. It reads the fingerprints of molecules floating in space. That means it can uncover hidden truths about a planet's environment. Truths that were always there but remained out of reach. For decades, Mars has been called the most likely place for human expansion. Scientists have studied its surface, its ice caps, and its weather. Rovers have explored its soil. Satellites have mapped its terrain. Step by step, a picture was built. Mars seemed harsh, but manageable. Its thin atmosphere was known. Its freezing temperatures were expected. Its dust storms were dangerous, but predictable. Engineers believed these challenges could be solved. With enough technology, humans could survive there. That belief shaped long-term plans. But Webb introduced a new layer of reality, and that reality is far more complex. When scientists analyzed the data, they noticed something unusual. The Martian atmosphere was behaving in ways that did not fully match earlier models. Heat distribution across the planet showed unexpected patterns. Certain gases appeared in fluctuating amounts. Changes were happening faster than predicted. This was not just new information, it was a warning, because survival on another planet depends on stability. It depends on knowing the environment well enough to prepare for it. Every system designed for human life relies on accurate data, air supply, radiation protection, temperature control, food production. If the environment behaves unpredictably, everything becomes harder and more dangerous. There's another detail that makes this even more concerning. Mars has almost no protection from space radiation. On Earth, a thick atmosphere and a strong magnetic field shield life from harmful cosmic energy. Mars lacks both. This was already known, but Webb's observations support the idea that radiation exposure on Mars may be even more intense and more complex than expected. Subtle atmosphere changes can affect how radiation moves and interacts with the surface. This means that future astronauts could face risks that are not fully understood yet. Long-term exposure to radiation can damage human cells. It can increase the risk of cancer. It can affect the brain and the nervous system. These are not short-term problems. These are mission-ending risks, and they cannot be ignored. Then there is the mystery of methane. Methane has been detected on Mars before, but the data has always been inconsistent. Some missions reported spikes, others found nothing. Scientists debated the source. Geological activity was one explanation. Chemical reactions were another. Some even considered the possibility of microbial life. Webb added new insight to this puzzle. Its sensitivity allows it to detect trace gases with extreme accuracy. Early observations suggest that methane on Mars behaves in unpredictable ways. It appears and disappears. It does not follow a clear pattern. This raises more questions than answers, because an unstable chemical environment can be a serious challenge for human survival systems. It means the atmosphere is not as simple as once believed. It means reactions could be happening that we do not fully understand. And unknown systems are dangerous systems. There is also the issue of temperature. Mars is already known for its extreme cold, but Webb data suggests that temperature distribution across the planet is more dynamic than expected. Some regions heat up and cool down faster than models predicted. This can affect atmospheric circulation. It can influence dust activity. It can change how energy moves across the planet. These shifts may seem small, but they have large consequences, because on Mars, even small changes can push conditions beyond the limits of human survival. Dust is another hidden threat. Mars is covered in fine, toxic dust. It can cover solar panels, it can damage equipment, it can enter habitats and pose health risks. Webb observations help scientists understand how dust interacts with heat and light in the atmosphere. And the picture that is emerging is not simple. Dust may play a bigger role in atmospheric instability than previously thought. It can influence temperature changes, it can affect visibility, it can trigger large-scale storms, and those storms can last for weeks or even months. All of this leads to a single question. Is Mars far more hostile to humans than we thought? For years, the focus has been on reaching Mars, building rockets, planning missions, designing habitats. The goal has been clear: get there. But Webb is shifting the conversation. Now, the question is not just how to reach Mars, the question is whether humans are truly ready to survive there. Because the more we learn, the more complex the challenge becomes. And complexity increases risk. In this video, you will discover what the James Webb Space Telescope has revealed about Mars. You will learn about the hidden dangers in its atmosphere, the invisible threats from radiation, the strange behavior of gases that scientists still cannot fully explain. You will also see how these discoveries could change the future of human space exploration, and why the dream of living on Mars may be far more dangerous than it seems. Stay with us until the end, because the final insight may completely change how you see humanity's future beyond Earth. Welcome to the channel. Subscribe now and explore the universe like never before. The power of the James Webb Space Telescope comes from something human eyes can never see. It does not rely on visible light. It studies infrared radiation. This is heat energy. Every object in space gives off this signal even in complete darkness. Planets, stars, gases, and dust all leave behind a thermal signature, and inside that signature lies a hidden code. Each chemical element absorbs and emits infrared light in its own unique way. This creates patterns that scientists call spectral fingerprints. By reading these patterns, Webb can tell exactly what a planet's atmosphere is made of. Not just the main gases, but even tiny traces that older instruments would completely miss. This is where things become serious, because Mars has been studied for decades. Orbiters have scanned its surface. Rovers have tested its soil. Previous telescopes have analyzed its atmosphere. Scientists believe they had a clear understanding of its composition. Webb was not expected to rewrite that knowledge. It was expected to confirm it. Mars was chosen as a test case for a reason. It is close. It is well studied. It is considered predictable compared to distant exoplanets. If Webb could accurately read Mars, it would prove that it could analyze the atmospheres of worlds light years away. In simple terms, Mars was supposed to be easy, a calibration target, a stepping stone. But the moment Webb began collecting data, small inconsistencies started to appear. At first, they seemed minor, slight variations in temperature readings, subtle shifts in how heat was distributed across the planet. These details might not sound important, but in planetary science, even tiny changes can reveal deeper problems. Then came the atmospheric signals. Webb detected carbon dioxide with extreme clarity. That was expected since Mars is mostly made of it, but the distribution was not perfectly uniform. Some regions showed variations that did not match earlier models. This raised a question that why would a thin, simple atmosphere behave in a complex way? Then scientists noticed something else. The way sunlight was interacting with the atmosphere did not fully align with predictions. Heat was being absorbed and released differently than expected. Certain layers of the atmosphere appeared more dynamic, almost active, instead of calm and stable. This was unexpected. Mars was believed to be a quiet planet, geologically slow, atmospherically weak, a world that had already lost most of its energy billions of years ago. But Webb hinted at movement, subtle but real. There were also early signals related to trace gases. These gases exist in extremely small amounts, sometimes only a few parts per billion. Older instruments often struggle to detect them accurately. Webb does not have that limitation. Its sensitivity allows it to pick up faint chemical traces that were previously invisible. And those traces did not always behave as expected. Some appeared in slightly higher concentrations, others seemed to fluctuate. These changes were not large enough to be obvious, but they were enough to challenge existing assumptions. This is where the concern begins to grow. Because if the atmosphere of Mars is more complex than believed, then every prediction based on it becomes less certain. Climate models, radiation exposure estimates, even basic survival calculations depend on stable and predictable data. And Webb was showing early signs that Mars might not be as simple as it once seemed. These were only the first observations, but they were enough to suggest that something deeper was happening beneath the surface of what we thought we knew. The data did not stay subtle for long. As scientists continued to analyze signals from the James Webb Space Telescope, the patterns became harder to ignore. What first looked like small variabilities began to form a larger, more troubling picture. The atmosphere of Mars was not behaving the way it should. Carbon dioxide dominates the Martian atmosphere. This has been known for years. It makes up more than 90% of the air. Because of this, scientists expected a relatively uniform structure, thin, simple, and predictable, but Webb saw something different. Instead of a smooth distribution, carbon dioxide levels showed subtle variations across different regions. Some areas appeared denser than expected, others slightly thinner. These changes were not random noise. They followed patterns that suggested movement and interaction. This was unusual for a planet with such a weak atmosphere. Then came the trace gases. These are the rare components, tiny amounts of molecules that exist in such low concentrations that they are often overlooked. But Webb does not overlook anything. Its sensitivity allows it to detect even the faintest signals, and those signals were not stable. Certain trace gases appeared to fluctuate over short periods of time. Their presence was not consistent. In some readings, they were stronger. In others, they faded or shifted. This suggested that chemical processes were happening faster than expected. Mars was not supposed to behave like this. Scientists believed its atmosphere changed slowly over long periods, controlled mostly by seasonal cycles and sunlight, not by rapid or unpredictable shifts. But Webb data hinted at something more active. Then there was the issue of heat. Infrared observations revealed how temperature was distributed across the planet. This is critical because heat drives atmospheric behavior. It controls wind patterns. It influences chemical reactions. It determines how gases rise and fall. And once again, the results did not match expectations. Certain regions were absorbing more heat than predicted. Others were releasing it faster. The balance was uneven. Instead of a steady flow of energy, there were signs of disruption. This affects everything because when heat moves differently, the entire atmosphere responds. Gases expand and contract, pressure shifts, circulation patterns change. Even small imbalances can create larger effects over time. It is like a chain reaction, and Mars seemed to be reacting. Another detail made this even more concerning. These changes were happening over relatively short timescales, not millions of years, not even centuries, but in ways that could be observed within current measurements. That means the environment is not just complex, it is active and possibly unstable. This challenges a long-standing assumption. Mars was thought to be a quiet world, a planet that had lost most of its internal energy, a place where age-old changes were rare and slow, but Webb revealed a different reality. A planet where the atmosphere still shifts, where energy moves in unexpected ways, where chemical signals rise and fall without clear explanation. This level of unpredictability is not just a scientific curiosity, it is a serious problem for human survival, because survival systems depend on stability. They depend on knowing how the environment will behave tomorrow, next week, next year. If the atmosphere cannot be fully predicted, then every plan becomes more fragile. Every calculation carries more risk. And the deeper scientists look into this data, the more they realize that Mars may not be as calm as it once appeared. There is a danger on Mars that no one can see. It has no color, no sound, no warning, and it can pass straight through the human body. Radiation, Mars has almost no natural protection against it. On Earth, life survives under a thick atmosphere and a powerful magnetic field. These two layers act like a shield. They block and deflect most of the harmful energy coming from space. Mars lost that protection billions of years ago. Its magnetic field faded, its atmosphere thinned. What remains today is only a small fraction of what once existed. The air pressure on the surface is less than 1% of Earth. That is not enough to stop dangerous radiation. This was already known, but new observations from the James Webb Space Telescope add a deeper level of concern. By studying how heat and energy move through the Martian atmosphere, Webb helps scientists understand how radiation interacts with it, and the results suggest that the surface is exposed to more complex and possibly more intense radiation patterns than expected. There are two main sources of this threat. The first is solar radiation. This comes directly from the sun. It includes high-energy particles released during solar flares and coronal mass ejections. On Earth, most of this energy is deflected by the magnetic field. Mars has no such defense. When a solar storm hits Mars, the surface is directly exposed. The second source is cosmic radiation. These are high-energy particles that travel across the galaxy. They move at nearly the speed of light. Some of them come from exploding stars. Others come from distant and unknown events in deep space. These particles are extremely powerful, and they do not stop easily. Webb data suggests that the thin Martian atmosphere does very little to slow them down. In some cases, when these particles hit the atmosphere, they create secondary radiation. This means one incoming particle can trigger a cascade of smaller but still harmful particles. This increases the overall exposure, and it creates a more complex radiation environment than a simple direct hit. For humans, this is a serious problem. Radiation at these levels can damage DNA. It can break the molecular structure inside cells. Over time, this damage builds up and increases the risk of cancer. It can affect the brain. It can lead to memory loss, reduced cognitive function, and long-term neurological issues. These are not immediate effects. They develop slowly, which makes them even more dangerous. An astronaut on Mars would be exposed every single day, not just during space travel, but while living on the surface. Even inside a habitat, some radiation would still get through. Engineers have proposed solutions: thick shielding, special materials, living underground, but none of these solutions are perfect. Building underground habitats sounds safe, but it comes with challenges. Digging into Martian soil is difficult. The ground is hard and frozen in many places. There are also concerns about structural stability and dust contamination. And even beneath the surface, radiation does know. Fully disappear. Some high-energy particles can penetrate deep layers of soil. Others generate secondary radiation that spreads in different directions. This means there is no completely safe zone. Another lesser-known issue is the effect of radiation on equipment. Electronics can fail under constant exposure. Sensors can give false readings. Systems that support life can degrade faster than expected. This creates a chain reaction of risk. Because on Mars, survival depends on technology working perfectly, and radiation works against that. The more scientists study this environment, the clearer it becomes that radiation is not just a background problem. It is a constant threat, silent, invisible, and always present, and it may be one of the biggest obstacles standing between humans and long-term survival on Mars. There is another signal coming from Mars that has confused scientists for years. Methane, it is a simple gas. On Earth, it often comes from living organisms. Microbes produce it. Animals release it. It is also created by geological processes deep underground where heat and pressure reshape minerals. That is why methane on Mars matters so much, because its presence raises a difficult question. Where is it coming from? Earlier missions detected methane in small amounts. Then it disappeared. Later, it appeared again. These spikes were not consistent. Some instruments saw them clearly. Others found nothing at all. This created a debate that never fully settled. Now, the James Webb Space Telescope has added new data to this mystery. Its infrared sensitivity allows it to detect gases with extreme precision. It can identify faint chemical signatures that older tools might miss. This makes its observations highly valuable. And once again, the results are not simple. Methane does not behave in a steady way on Mars. It does not spread evenly through the atmosphere. It does not remain constant over time. Instead, it appears in sudden bursts. Then it fades, sometimes quickly. This is strange because methane should break down under sunlight. On Mars, ultraviolet radiation from the sun destroys methane molecules over time. Scientists expected any methane released into the atmosphere to slowly disappear in a predictable way, but that is not what the data suggests. Instead, methane seems to rise and fall in ways that do not follow a clear pattern. This means something is either producing it intermittently or destroying it faster than expected. Both possibilities are concerning. One explanation is geological activity. Deep beneath the surface, chemical reactions between rock and water could release methane. This process is known on Earth. It does not require life. It only requires the right conditions. But Mars is thought to be mostly inactive today. Its internal heat is much lower than Earth's. Large-scale geological activity is rare. So where would this methane be coming from? Another possibility is unknown chemical reactions. The Martian soil contains reactive compounds. Some of these can interact with sunlight and atmospheric gases. These reactions could create or destroy methane in ways that scientists do not fully understand yet. This would mean the chemistry of Mars is more active than expected, more unpredictable. Then there is the most controversial idea, microbial life. On Earth, certain microbes produce methane as part of their metabolism. If similar organisms exist beneath the surface of Mars, they could explain the sudden spikes. Protected from radiation and extreme temperatures, these microbes would remain hidden. Only their chemical signature would reach the surface. There is no direct evidence for this. But the possibility remains, and that alone makes methane one of the most important signals on Mars. There is enough. Their problem, if methane levels are unstable, it suggests that the atmosphere is not in chemical balance. It means reactions are happening that are not fully understood. It means the environment is active in ways that are difficult to predict. For human missions, this is not a small detail because life support systems depend on stable chemistry. Air processing systems rely on known reactions. Filters and converters are designed based on expected conditions. If the atmosphere behaves differently, those systems could face unexpected challenges. Even small chemical changes can affect how oxygen is produced, how carbon dioxide is removed, and how contaminants are managed. And on Mars, there is no room for error. The deeper scientists look into methane, the more complex the picture becomes. It is not just a gas, it is a signal, a sign that Mars may still be changing, reacting, and evolving beneath its silent surface. The deeper scientists study Mars, the less predictable it becomes. For a long time, Mars was described as a frozen and quiet world, a planet where change happens slowly, a place where conditions remain mostly stable from day to day. But that picture is starting to break. Data linked to observations from the James Webb Space Telescope suggests that Mars is far more dynamic than expected, not in obvious ways, but in subtle shifts that add up over time. One of the most striking features is temperature. Mars does not just stay cold, it swings between extremes. During the day, temperatures near the equator can rise above freezing. At night, they can drop to levels far below minus 100 degrees Celsius. This change happens quickly. There is very little atmosphere to hold heat. On Earth, air acts like a blanket. It traps warmth and spreads it around the planet. Mars lacks this protection. Heat escapes rapidly into space. This creates sharp and sudden changes. And those changes affect everything. Materials expand and contract. Equipment experiences stress. Systems designed to operate at one temperature must suddenly handle another. Over time, this can lead to failure. Then there is the weather. Mars does not have rain or oceans, but it does have wind, and that wind carries dust. Martian dust is not like dust on Earth. It is extremely fine, almost like powder. It can stay suspended in the air for long periods. It spreads across vast distances. It covers everything it touches, and it does not just sit there. It interacts with sunlight. When dust fills the atmosphere, it blocks and scatters light. This changes how heat is absorbed by the surface. Some areas receive less sunlight. Others trap more heat in the air above them. This creates imbalances, and those imbalances can grow. Small dust events can turn into massive storms. Some of these storms can cover the entire planet. They can last for weeks, sometimes even longer. During these storms, sunlight drops dramatically. Solar panels lose power. Visibility becomes almost zero. Temperatures shift in unpredictable ways. This is not a rare event. It is part of the Martian climate. Webb data helps scientists understand how dust, heat, and atmosphere interact on a deeper level. It shows that these systems are more connected than once believed. A change in one part of the planet can influence another. This makes the climate harder to predict. Earlier missions provided valuable data, but they had limitations. They could not always capture the full picture of how energy moves through the atmosphere. Webb adds another layer of detail, and that detail reveals complexity. Mars is not just reacting to sunlight, it is responding through a network of processes that are still not fully understood. Heat moves differently. Dust behaves unpredictably. Atmosphere layers interact in ways that models did not fully capture. For human survival, this creates a serious challenge. Life support systems depend on stability. They rely on predictable inputs, air pressure, temperature, energy supply. All of these must stay within safe limits. But on Mars, those limits can shift. A sudden drop in temperature can affect internal systems. A dust storm can reduce power generation. Changes in the atmosphere can influence how heat is managed inside habitats. This means that every system must be prepared for constant change, not just extreme conditions, but changing conditions. And that requires a level of resilience that goes beyond current designs, because on a planet like Mars, the environment is not just harsh. It is unstable. All of these discoveries lead to one unavoidable reality. Reaching Mars is only the beginning. Surviving there is something entirely different. For years, missions planned by NASA and other space agencies have focused on transportation, powerful rockets, long-duration travel, safe landing systems. These challenges are already complex, but the environment waiting on Mars may be even more difficult because every new piece of data adds another layer of risk. Radiation is stronger and more unpredictable. The atmosphere is less stable. Chemical behavior is not fully understood. Temperature swings are extreme. Dust can disrupt entire systems. Each of these problems alone is serious. Together, they create a chain of challenges that must all be solved at the same time. This changes how missions need to be designed. Habitats can no longer rely on simple protection. They must include advanced shielding to block radiation, not just from one direction, but from all angles. Materials must be stronger, thicker, and more resistant to long-term exposure. This adds weight, and weight increases cost. Life support systems must also become more advanced. Air must be carefully managed in an environment where atmospheric behavior is not fully predictable. Oxygen production, carbon dioxide removal, and pressure control must all operate with extreme precision. Even small failures could become life-threatening. Energy systems face similar risks. Solar panels are one of the main power sources planned for Mars missions, but dust storms can block sunlight for long periods. Fine particles can cover surfaces and reduce efficiency. In some cases, power levels could drop to dangerous limits. This means backup systems are essential. More systems mean more complexity. More complexity means more points of failure. There is also the issue of long-term exposure. A short mission is one thing. A permanent presence is something else. Astronauts would need to live on Mars for months or even years. During that time, they would face constant radiation, isolation, and environmental stress. Human bodies are not designed for this. Muscle loss, bone density reduction, psychological strain. These effects are already seen in space. On Mars, they would combine with new and unknown risks. Another challenge is maintenance. Every system on Mars must be repaired using limited resources. Spare parts cannot be easily delivered. Tools must function in extreme conditions. Dust can interfere with mechanical components. Temperature swings can weaken materials over time. This means that reliability is not optional. It is essential, and yet complete reliability is difficult to achieve. All of this leads to a major shift in thinking. Mars is no longer just a destination. It is a test of human limits. The cost of building systems that can handle these conditions is far higher than earlier estimates. The technology required is more advanced. The risks are greater, the margin for error is smaller. Every mission must now account for factors that were once underestimated. And this raises a critical question: are we moving forward with a full understanding of what Mars really is? Because the more scientists study it, the more it reveals a deeper level of complexity. And complexity in space is often the difference between survival and failure. The James Webb Space Telescope did not just look at Mars, it revealed it, not as a simple red desert, not as a quiet frozen world waiting for human footsteps, but as a place filled with hidden dangers, a place that behaves in ways we are only starting to understand. The atmosphere shifts more than expected. Radiation cuts through the surface without mercy. Chemical signals rise and fall without clear answers. Dust and temperature create a system that refuses to stay stable. This is not just a harsh environment. It is an unpredictable one. For years, Mars has been seen as the next step for humanity, a new home, a backup plan, a symbol of progress. But the deeper we look, the more we realize that this planet does not welcome life easily. Every solution creates new problems. Every discovery reveals new risks. Survival on Mars is not just about building better machines. It is about pushing the limits of human endurance. It is about surviving in a place where even small mistakes can become fatal. This changes everything, because reaching Mars is no longer the ultimate challenge. Understanding it is. Said right now that understanding is still incomplete. There are still unknowns hidden beneath the surface, still processes we cannot fully explain, still dangers we may not see until it is too late. Humanity stands at the edge of something extraordinary, but also something uncertain. Before we take the next step, one question remains: do we truly understand what we are walking into? If this made you think, take a moment to like the video and subscribe to the channel for more deep explorations into space, science, and the unknown, because the universe always has more to reveal.